let's say f of t equals hyperbolic. I don't want to work on hyperbolic secant. I'm just going to change that. Hyperbolic cosine squared of e to t. So f prime will be 2 hyperbolic cosine of e to t times the inner function prime. I have to subtract 1 from the power. I did already. Times hyperbolic cosine prime, which is hyperbolic sine of e to t, times the inner function prime, which is e to t. And yes, we can rearrange the order, but it's not going to make any difference. Any questions? Let's look at one more, like f of x equals hyperbolic tangent 1 plus e to 2x. Okay, so then f prime, hyperbolic tangent is hyperbolic secant squared of 1 plus e to 2x times the inner function prime, which is e to 2x, times the inner function prime, which is 2. Any questions? Any questions? Okay. If you have nothing for me, then I would like to continue with 3.10, and then hopefully I get to talk about the marginal cost. 3.10, linear approximations and differentials. I think in this section you're going to realize how great calculus is, I hope. I'm not going to start with linear approximations. I'm going to start with differentials. Differentials. And after that, I can go to marginal cost, back to 3.7. Okay. Let's take a look at this function. Here is f of x. And I have a point on this graph. Point is P. You know the drill. I have x, of course. You already know I was going to ask about that, and you're going to have to say P f of x. And I have a point Q here. And yes, you already know what will be the x coordinate of Q.
A.
Right. X plus a little bit, right? So this is our little bit. But this time the little bit, this was what we had in the past. This time the little bit will not be denoted by h. It will still be a little bit, but it will be denoted by dx or delta x. And you can say, wait a minute, what's with this delta? This is the lowercase delta. This is the uppercase delta. Okay, not to be confused from the formal definition or the precise definition of the limit. And this is a different delta. So this time we're not going to call this h. This is what we are used to seeing, h. But this time we're going to call it dx delta x. They are the same. Dx equals delta x. So then, of course, can anyone give us the y coordinate of q?
F of x plus delta x.
F of x plus delta x or f of x plus dx, they are the same. Perfect. Thank you. Okay. So stay with me. This is Not complicated, but I just want you to pay attention. Now, imagine that I have to produce these erasers. And I measure the length. And I realize that the machine has an error. It should be 5 inches long, but there is a tiny error in the length. The machine is not creating them at 5 inches long. There is a tiny error. This is the error. So imagine that dx is the error in x, whatever I'm measuring. If x is the length, then it's an error in the length. Tiny error in the length. But I hope you agree that if I have a tiny error in the length of the eraser, that will trigger an error in the volume. So if it's not long enough, or if it's shorter than it should be, the volume will have a difference, will have an error itself. Imagine that the function is the volume, and the length of the eraser is the x value. Oops, I didn't even write the x here, x and y and 0. Okay, so the length is x, the volume is the function. So because I have an error in the length, that will trigger an error in the function. So what will be the exact error in the volume, if you want, or in f of x? Let me write it as lowercase. Exact error in f of x produced by delta x or dx. Can anyone tell us? Look at the graph and say, I know. If there is an error in x, there will be an error in y, and the exact error will be determined, and it's denoted by delta y. Exact error in f of x produced by delta x equals dx. So can anyone look at the graph and tell me what is the formula for delta y?
Is it going to be f of x plus dx minus f of x?
Brilliant. Thank you. So it's f of x plus delta x minus f of x. Is this distance between this point and this point? This is it. This is delta y. The exact. Excellent. Now, follow me, please. Okay. Nothing new. This is just algebra. I didn't do anything, right? But now I'm going to draw a tangent at P. And I'm going to extend the tangent. So this is the tangent at P. I'm going to extend this vertical. I didn't mean it to be right there on the line. It just happened. And I'm going to create this right triangle. Notice one thing. This is very small. Q is very close to P. You understand that I zoomed in. And this looks huge. No, 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 no. Q is very close. Dx and dx delta x are very small. Q is right here. So we're not talking about something like this, because dx is small. So Q is right here. So I have to zoom in in order to explain what I'm doing. Okay. Now, is there a way of determining the slope of this line from what we covered so far in this class?
That would be delta y over delta x.
Delta y is this piece. Delta x is this piece. That cannot be the slope of this line. Anyone? Gia, Ian, I haven't heard from you. Kaylin, Sarah, Oscar.
Would you treat it as a right triangle?
Say it again.
Would you treat it as a right triangle and then?
In this class, we haven't talked about triangles. From the very beginning and the entire semester so far, we talked about something else. What did we do here? How did we determine the slope of the tangent here?
You need to find the derivative at point P.
Thank
right?
you. Thank you. So, who said that?
Carson.
Thank you. So the tangent at P has a slope f prime of x. This is the slope of the tangent at P. Is there another notation that we used several times in the past few weeks instead of f prime of x?
It's going to be the d over dx, or dy over dx.
Good. Very good. So now let's go back to our triangle. So the slope of this line is f prime of x. But in any triangle, the slope of this line, the hypotenuse, is rise over run. So the slope of this line is rise over run. But this is the rise, which is not delta y. This is the rise, and this is the run. So this is dx. This is f prime, right? The slope of this line is f prime. And f prime of x equals dy over dx. So this is dx. Then what could this be?
dy.
Exactly.
dy.
Exactly. This is dy. Again, q is very close to p. So I would say from here I would like to determine dy. Can anyone tell us how to solve this for dy? And you could say, stop. You never told us that these two have meanings separate by themselves. You never said that to us. I didn't, because I couldn't till this point. So this is a notation for the derivative. This is a notation for the derivative, but also these two pieces have meaning on their own, by themselves. So how will I determine from this equation dy? And I will tell you what dy represents. Anyone? This is algebra now.
Multiply each side by dx.
Thank you very much. F prime of x dx. So remember, this was the exact error. This dy is not the exact error. Is the differential of f of x, which is the approximate error using, which is determined using the derivative. What is dx? The differential of x. The error in x. Okay, now can anyone give us the relationship between delta y and dy? Before you say anything, let me refresh your memory one more time. Q is here. Again, this is delta y. This is dy. I want a relationship between these two. What will be the relationship between the exact error and the approximate error? Using the derivative, and this is using algebra, this is using calculus. What do you think I should write between the two of them? What symbol?
Is it delta y is less than dy?
We don't know.
Can you write the approximately symbol?
Exactly true. They have to be very close because this point is here and the delta x is very small. So delta y is the exact. It can be approximated with dy as long as dx, delta x are small. Very good. Now, before we continue with the problem, to cement this concept,